Today, on How It's Made. Goalie pads. The puck stops here. Lapel pins. Allegiance made to order. Cardboard boxes. A product that's all packaging. And crystal wine glasses. The science behind the sparkle. In 1896, George Merritt of the Winnipeg Victorias was the first ever hockey goaltender to wear pads to protect his legs during the Stanley Cup playoffs. He and those who followed him used cricket pads. Wider pads specifically for ice hockey didn't come about until the 1920s. This company spends $40,000 a year on research and development of goalie pads. It redesigns its pads every 2 years to upgrade to the latest materials and construction. Each goalie pad has 100 components. The factory uses hundreds of metal dies to cut parts to make pads in 15 sizes. Workers position the appropriate dies on the material. A hydraulic machine applies roughly the weight of 4 elephants, forcing the dies through up to 4 layers at once. Here, it's a synthetic water-repellent material called PU leather. The machine also cuts various types of foam for structure, protection, and comfort. And it creates holes called eyelets for laces or buttons. Here, the machine cuts soft, low-density foam, which acts as a shock absorber against the force of the puck. Workers sew the pads using industrial-strength nylon stitching. To protect the PU leather, they sew on a 3mm layer of foam and zippers on openings that will be packed with shredded foam for a snug fit. They use a 1.2 centimeter thick layer of spongy foam to line the player's knee and calf areas for flexibility and comfort. The stitching is purely decorative. The factory often embroiders the player's name on the goalie pads to identify the gear if it's lost. This automated embroidery machine has 12 computer-guided heads. They use up to 40 different thread colors. Every year, this factory produces up to 3,500 pairs of goalie pads. The players wear an array of corporate logos on their pads. It's all part of the commercial nature of the game and the industry. Now they sew on a zippered pocket which, when filled with foam, will protect the calf area. They use water-resistant fabric to cover the back of the player's leg and line the area with low-density foam to absorb the puck's impact. Then they attach flaps called knee raisers to protect the knee area. Good thing, given that pucks will slam the goalie at a speed of up to 160 kilometers an hour. Next, they sew the front and back parts of the pads together. Then they hot glue a sandwich of harder foam for structural support, soft foam for shock absorbency, and an even softer foam for comfort. This padding forms the guts of the pad. Using crimpers, workers fasten the pads together temporarily. Then they use an 18-centimeter long needle with a diamond-shaped tip to sew the layers together. The worker threads the layers, uniting them into one piece. This process is called lasting. Workers now pack the outside of the goalie pad with more rigid foam for structure and softer foam for comfort. They use clamps to fasten the boot area together temporarily while inserting shredded foam. Shredded because it's easier to squeeze in. Then, using a specialized sewing machine, they sew the outermost shell of the pad. This is considered the toughest part of the assembly, since it joins layers as thick as 2.5 centimeters. They use pliers to hold the pieces tightly together during the 45 minutes or so that it takes to sew just one pad. After trimming the excess from the ends, workers cover them with a strip of PU leather, a process called capping. They attached a strip using 13 overlapping stitches, a durability feature that gives the goalie pads long life. Next, they insert a removable knee guard, which can be adjusted or replaced later on. Using a rivet machine, they attach a leather strap to an adjustable nylon buckle. It's an important component. This is what fastens the pads to the leg. And at a price of nearly $1,600 a pair, you too can shut out those speeding pucks with confidence. Lapel pins let you proudly show off where you've been or where you stand. From an event you've attended or your political beliefs to your professional affiliation or your favorite sports team. Lapel pins cost pennies to produce, but some are collector's items worth thousands of dollars. They may be tiny, but they're out there in huge numbers. This one company turns out about 5 million lapel pins a year. It all starts with a sketch of the pin design, and from that, the master, a negative made of magnesium, a type of metal. They'll make copies of this master to create a production mold. But first, using what's called a coping saw, they cut out the front and back pieces of the master. Using a dispenser about the size of a sewing needle, they glue the pieces together with epoxy. It takes 5 minutes to dry. Then they cast enough copies of the master to fill up a rubber disc. After tracing the outlines, a worker uses a surgical knife to meticulously carve out the cavities. He softens the rubber with paint thinner to enable precision cuts. Then he places a copy of the master in each cavity. Another disc goes on top. Then it's into a machine called a vulcanizer for 1 hour. This machine uses heat and pressure to cure the rubber, making it as hard as a car tire. It also melds the rubber around each master copy, embedding the detail. This will be the production mold for producing this pin design. Now, using a surgical knife again for precision, they carve out sprues, channels that during the casting process will direct the flow of molten metal to the cavities. They also make smaller, curved channels called runners to filter out any air or dirt particles. It's crucial to position the sprues and runners correctly because this mold produces an entire line of a particular pin. Mess up and they'd have to remake the mold from scratch. Next, they insert a centimeter-long brass tack called a post into each cavity. It'll later fasten to a clasp, attaching the pin to clothing. The post goes in now rather than later so that it will fuse to the back of the lapel pin during casting. Now to close the mold, they align the buttons on one half with the depressions in the other half. The mold then goes into what's called a spin casting machine. Using a cast iron ladle that can withstand the fiery temperature, they pour in molten metal, either pewter, zinc, or a tin alloy. As the machine spins, centrifugal force propels the metal into every nook and cranny of the cavities. After a minute of spinning, 400 rotations, the mold comes out. The metal takes about 5 minutes to cool and harden. The factory remelts the excess metal for the next batch. Next, a brass clasp called a clutch goes onto the post. Now the lapel pins go for an hour-long wash in soap and water and abrasive stones. The stones smooth out any rough edges. The pins go into the electroplating tank for a surface coating of metal. How many coats and the types of metal vary with the design. An electric current draws the metal particles onto the pins, plating them thoroughly. These pins first get copper plating, then nickel plating, then gold plating. Now it's time to paint the lapel pins. Workers follow a numerical guide, like a paint-by-numbers kit. They paint each pin individually using minute quantities of epoxy paint. They control the paint syringe with a foot pedal. Once the paint dries, a machine called the pad printer gathers up ink and stamps on the tiny details, the ones too small to paint by hand. Pierce the post through the fabric, secure it with the clutch, and this lapel pin is now ready to wear. Like many inventions, the cardboard box was born by sheer accident. In the 1870s, an American printer by the name of Robert Gare stumbled upon the idea. By mistake, he cut a paper seed bag he was creasing with a metal ruler. Gare concluded he could create a sturdier container with paperboard. Now that was thinking outside the box. Cardboard boxes come in a wide variety of sizes, shapes, and colors, but most share three basic structural components. One wavy sheet of paper, called the flute, sandwiched between two flat sheets called liners. Together they form what's called a corrugated board. Production starts with a massive roll of partially recycled paper. The width of the paper varies depending on the size of the boxes they're making. The roll feeds a machine called a corrugator. The machine presses the paper between two ridged rollers and blasts it with hot steam. This shapes the waves of the flute. Another roller applies glue to one side of the flute. The glue's main ingredients are water and starch, which won't contaminate fresh produce the boxes may later contain. Next, the machine adheres one liner sheet and then the other. The waves create an air cushion between the flute and the liners, strengthening the board. For added strength, some boxes have a double lining, 2 flutes and 3 liners. The flutes may also vary in thickness for more or less cushioning. The factory uses partially recycled paper for the flutes because it's more malleable than non-recycled paper. A razor-thin circular saw trims each side. The corrugator machine then cuts the board up to 9 times, depending on the size of the box they're producing. The corrugator's final function is to separate the boards into layers using flexible aluminum tongs called fingers. Workers do a quality control check before sending the boards off for printing. The next machine stacks the boards into piles of between 25 and 80, depending on their thickness. This machine also feeds one board at a time to the upcoming equipment. It does this at lightning speed, at a rate of up to 8,000 boards per hour. First, a trimmer perforates the boards to create flaps and handles. Rubber sponges cushion the blades so that they cut only the parts they're supposed to. During the trimming, a press condenses the box's overlapping panels to level out their thickness. Workers usually cut the sponges by hand to make sure they fit snugly around the blades. The trimmer runs at a speed of 8 kilometers an hour, processing up to 90 boxes per minute. Workers send the cut-offs back to the paper mill to be recycled as many as 6 times over. A folding machine now bends them along score lines the corrugator made earlier. It then applies cold glue to the sections that'll join together to form the box. Hot glue if the cardboard is wax-coated. The next machine folds over the glued sections. They aren't visible once the box is finished. Another machine stacks the boxes in piles. A separator arm moves the bundles to trays called skids for shipping. The printing of the boxes began in the factory's ink kitchen. A computer-guided dispenser squirts out different shades of ink, following a precise recipe to create a particular color, one of 5,000 in the palette. One pail holds about 20 kilograms of printing ink, enough for about 2,000 boxes, depending on the coverage needed. The factory uses water-based ink because it dries instantly. The printing press applies the ink to the boards, one color group at a time, through 4 consecutive stations. This factory uses a flexographic printing system, a process that can print drawings and illustrations. Some companies use a lithographic press, which can also print photographs. Back on the trimming line, more complicated types of box flaps and handles require what's called a flatbed trimmer. It holds the boards in place with suction while making intricate perforations. After removing the trimmed bits, workers give the boxes one last quality check. Then they stack them and send them off to the warehouse. The main ingredient in glass is silica sand. When you heat it along with other chemicals, it turns into a syrupy liquid that you can then mold or blow into a particular shape. Add lead oxide and you've got lead crystal. It's much softer than regular glass, making it easier to decorate with intricate cut designs to enhance its brilliance. Craftsmen start with silica sand, which is a very pure type of sand. Then they add nickel oxide to help the silica sand melt, lead oxide, potassium carbonate, potassium nitrate, and antimony to give the finished crystal its smoothness, heft, and sparkle. They compress the mix into pellets. They heat the pellets for 18 hours, creating a mass of molten glass that they call the melt. To that they add cullet, the term for excess, broken, or rejected crystal. Cullet smooths out the melt. A blower now uses a hollow blowing iron made of tempered stainless steel to collect some of the melt. He constantly rotates the iron so the melt clings together in what's called a gather. The blower rolls the gather on a heat-resistant table. This sparks a flame because the table is coated with beeswax to prevent the molten crystal from sticking. The blower exhales a slow, steady breath of air to create the base of the piece called the ball. After letting it cool for 90 seconds, he dips the ball back in the furnace to coat it with another layer of molten crystal. This fortifies the ball. Now he begins shaping the ball using various wooden tools. This one's called a block. He uses another tool, a divider, to create grooves so the ball will fit into a mold. The blower soaks the wooden tools in water so they won't burn. He now inserts the ball into a steel mold, one of 150 this company uses for its collection. The craftsmen coat the inside of the mold beforehand with a paste of cork dust, linseed oil, and charcoal dust. This prevents the ball from sticking, which would cause flaws in the crystal. The blower releases the ball, now called the bowl, using a foot pedal. After cooling the bowl for 1 minute, another craftsman, called a stemmer, adds another gather to create the stem of the wine glass. He clips the gather with heat-resistant scissors. He uses a wooden divider to shape the stem area, and a metal divider to stretch the gather into the shape of the stem. The stemmer must be highly skilled. There's no mold or pattern to follow. He relies entirely on eyesight, intuition, and patience. He cools the stem with layers of wet newspaper. They absorb heat well and don't leave marks or flaws. Next, another craftsman adds more gather to create the foot of the glass. He uses a wooden tool called the pitch to flatten the foot. He also shapes the foot by hand with wet newspaper. This metal template ensures it's generally the right dimensions. Everything is handmade, so each piece may differ slightly. This company makes 20 models of glasses, including different styles for red, white, port, and ice wines. The piece then goes into a kiln at 450 degrees Celsius. At the end of the day, they switch off the kiln to let the glasses gradually cool overnight to room temperature. The next day, a craftsman uses an acetylene torch to cut the glass and remove the cap. They use an old record turntable to spin the glass around and make the cut. For precision, they smooth and bevel the rim with a diamond-coated steel grinder. Another craftsman, called a cutter, marks out a grid with a waterproof pen. He uses another type of turntable to steady his hand as he draws. It's not an exact pattern, just a general guideline to create the design of the piece. This design's called the Titanic. It's based on a light fixture from the ocean liner. Water cools, lubricates, and cleans the area during cutting. There are two types of cutting, wedge and flat. Wedge cutting creates the deep, intricate cuts. Flat cutting creates smoother, less angled cuts. Here they use the wedge method, which can only be done with diamond-tipped wheels. Here the cutter creates a diamond-shaped grid called a carrow cut. Finally, the cutter creates a star-shaped cut spanning the entire foot of the glass. Once the decorations are complete, an inspector does a detailed quality check before etching the company logo. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.net.